my task here is to give you an introduction on supersymmetric gauge theories and AdS CFT. And the transparencies, or the copies of the transparencies, I think are available to you. I've seen them float around. There also is a fourth lecture, which I will give to Susan soon, so that she can also Xerox it. I thought actually these things would be left on a website so that you don't print out all this paper and kill trees, but I guess the University of Colorado is not that environmentally friendly. Okay. Now, the other thing is also that, in fact, I was asked a number of years ago in 2001 to give a similar set of lectures on AdS CFT. So, in fact, there is a set of lecture notes, which is authored by Dan Friedman and me, of the 2001 TASI lecture notes. And they're online. They're also on my UCLA homepage, so you can print them out. And that's about pretty much all that I wanted to say as an introduction. So supersymmetric gauge theories and AdS CFT. So let me immediately start with defining what we're talking about here. The AdS CFT conjecture stands for anti-de Sitter conformal field theory conjecture. And what it is about is a conjectured correspondence between two objects. The first one is four-dimensional n=4 superconformal Yang-Mills theory with some gauge group, SUN, let's say, to be concrete, and Yang-Mills coupling G Yang-Mills. And also there is a familiar instanton angle. And its multiplet of fields is given here. There is a gauge field A. There is, do you have a pointer? In fact? Right. I actually have my, yeah, I actually have my own pointer. The gauge field A, there are 4 Weyl fermions, lambda, and 6 scalars, xi. And this altogether forms the n=4 supermultiplet. So that's the first object. And the second object is something quite different. It's a 10-dimensional string theory, actually type 2B string theory, on a peculiar manifold, AdS5 cross S5. S5, you all know what it is, I think, the sphere of dimension 5. And AdS5 is simply its hyperbolic counterpart of negative constant curvature. Now, this is a complicated theory. We'll come to it a little bit later. But I can, for example, give you a description of its massless fields, particularly its massless bosonic fields, which is, in fact, type 2B supergravity. And that includes the metric, a dilaton, an axiom, and a lot of other stuff, which we'll come to later. Now, Maldacena actually conjectured precisely about slightly less than 10 years ago that these two objects are the same. Namely, that there's a one-to-one correspondence between states and any sort of extended objects as well. And I think I am not lying or exaggerating if I say that this conjecture is the most important development in theoretical physics in the last 10 years. It has simply revolutionized the field, and so that's in fact what I want to talk about. Now, I'm not going to assume that you are all familiar with these objects. Probably some of you are, and in that case, my lectures may be redundant. But then I would simply encourage you to consider this like a piece of music that you now hear from a different performer. Okay. Thank you. Wow. Okay. Now, actually, to make this correspondence more precise, there are a certain number. I'm going to get exercise from my right arm here. There is a definite correspondence between some of the quantities on the top of the slide and some of the quantities on the bottom. For example, the top depends on what the n is of SUN, and actually on the bottom there is a similar n dependence, which now is a topological charge of a certain rank 4 antisymmetric tensor field through the 5 sphere. And similarly, on top there is a Yang-Mills coupling, and this also has a correspondence on the bottom, namely it is in fact precisely equal to the string coupling for the string theory. And finally, these spaces are spaces that have some radius, some physical radius r, and that radius also has a correspondence and is linked to the coupling constant times n times alpha prime, which is essentially related to Newton's constant. Now, this correspondence is a conjecture, okay? It is not proven. In fact, it is interesting to think for a minute what it would mean to prove it. You are, of course, all used to certain conjectures in mathematics, like Fermat's theorem, which was really a conjecture until Andrew Wiles proved it, and the Riemann hypothesis, which is another conjecture. But at least those conjectures, their statements are clear. Their statements are on objects that we know to exist. In this case, both of these objects are really not mathematically known to exist. There is no proof that Yang-Mills theory or super Yang-Mills theory actually is a mathematically constructible thing, and there is no construction mathematically either of what string theory is, whether it be on AdS 5 cross S5 or anywhere else. So in fact, this is a conjecture in the physics sense, namely it's a conjecture between two things we don't really know how to define, you know, in a mathematical way, but we know how to define them in a physical way. So what is the motivation for this? Well, since I've told you already that this is probably the most important theoretical advance in the last 10 years, clearly there's a very long list of motivations, but I will give you just a few so as to whet your appetite. So basically the motivation is that, well, we fairly well understand Yang-Mills theory perturbatively and string theory perturbatively, but we do not really understand them very well non-perturbatively. So on the non-abelian gauge theory side, there are phenomena like confinement in QCD, like chiral gauge theories and their dynamics, like the dynamical breaking of symmetries, that may be supersymmetry or internal symmetries. All these things are to some degree understood, but not really very well understood, and certainly it would be very nice to have an improved understanding. On the superstring side, well, the problem is, of course, that string theory lives in 10 or possibly 11 dimensions, and we would like to understand this mechanism of compactification to our 4 dimensions better. We need to understand how and why supersymmetry is broken, because we are not supersymmetric as we sit and stand here. So we need to understand that. And also, very important is actually all the gravitational aspects of string theory, namely, for example, the fate of singularities or apparent singularities as we encounter in black holes. So the hope is, and it has been borne out to some degree over the last 10 years, is that a problem, for example, in gravity may actually turn out to be simpler if it is mapped to an analogous problem in conformal field theory, or vice versa. And so that's in fact the hope. This is coupled with the fact that, well, perhaps some of these Yang-Mills theories admit some degree of solvability, and I will explain more what I mean by that. We are used to this in 2 dimensions, for example, conformal field theory in 2 dimensions or integrable systems, but it is unlikely but possible that maybe in 4 dimensions too there is some degree of integrability. And in fact, there has been quite a bit of progress on this, and I think David Berenstein will actually talk about some of this in his lectures, I think 2 weeks down the line. So even if we cannot solve Yang-Mills theory or super Yang-Mills theory exactly, the next best thing is we can look at it in certain limits. For example, the large number of color limits, which is so-called 't Hooft limit. We will see that there is a further limit one can consider. Also, we want to deal with QCD, but that may still be too hard, so one can maintain more symmetry, which keeps us farther from supersymmetry, but nonetheless gives us enough understanding of the dynamics so that then we can later perturb the very supersymmetric theories and arrive at supersymmetric QCD or even QCD without any supersymmetry. We will see that, in fact, this correspondence is a strong weak coupling duality. A little bit like in the two-dimensional Ising model, you remember probably that the dynamics of the Ising model is invariant under a duality transformation where the temperature goes into 1 over the temperature. So this is somewhat similar. So in these two slides, I basically have laid out what the problem is, and then here is the list of the lectures I was planning to give. So in the first two lectures, I'm basically going to introduce supersymmetry, super Yang-Mills. That's the first part of the Maldacena correspondence. And in the second part, in the second lecture, I will introduce type 2B supergravity and superstrings, D-branes, and the Maldacena limit. Of course, that is a lot to do in one lecture, but we'll see how it goes. Then in lecture 3, we're actually going to get our hands dirty and see how concrete calculations, for example, of correlation functions or Green's functions, can be carried out on both sides and in certain cases compared, in the cases where we have non-renormalization of certain quantities. Now, originally there was some fourth lecture, which is the case when you have correlation functions without non-renormalization theorems, which I will not give, but on the other hand, I will ask Susan to put it on the website so you can look at it. And then the fifth lecture is actually going to be some another direction of application to some very recent work in collaboration with Michael Goodpearl and also John Estes, who is here, I'm sitting on the first row. And there we will consider a very slight deviation from the original setup in which we add an interface, and we'll see that that is actually, to a large extent, sort of a solvable model. So that's the plan for the lectures. Are there any questions at this point? You are free and welcome to ask questions at any time. Okay, you're all with me? That's good. So let's begin with the beginning, which is we are going to discuss supersymmetry basically throughout. And so let's be specific about what we mean, and I think for many of you this will simply be a review. So I'm going to start with 4 dimensions, familiar 4 dimensions, and the Poincaré group is simply the group of translations times semi-direct product with Lorentz transformations, and here they're generators. And so supersymmetry enlarges the Poincaré group to include also fermionic generators that map fermions to bosons and bosons to fermions. And so that means that the charges, the supersymmetry generators, are in fact spinors. And I'm going to use a convention in which they are Q sub alpha is the left Weyl spinor of 2 dimensions, and Q bar alpha dot is a right Weyl spinor, which is really just a complex conjugate of the other spinor. We're going to allow ourselves to not just extend the Poincaré group by 1 supersymmetry, but in fact by this number curly n, which is some integer. Could be 1, could be 4, and we'll see what the limits are. So altogether, with the Poincaré generators, these supercharges form an algebra, in fact a super Lie algebra, which is given like so. So the charges are translation invariant. I did not write down all the commutation relations. You know that Q is a spinor, so that tells you what the commutator is of L with Q, so I didn't write it down. It's totally straightforward. But the important ones are that Q and Q bar close on the momentum. Sigma here are the components of the two by two components of the gamma matrices. And the anti-commutator of two Qs, not of a Q and a Q bar, but two Qs, in general, by Lorentz invariance, are proportional to the epsilon tensor in spinor space. So this is the totally antisymmetric object in two dimensions, times a central charge matrix. So by the symmetry of the anti-commutator and the anti-symmetry of epsilon, Z is actually by construction an antisymmetric matrix of dimension n by n. And these objects are called the central charges. Central here means that they commute with everything else. Now clearly if you have n equal 1, which is the simplest supersymmetry, for example, it's the supersymmetry that enters into the minimally supersymmetric standard model, then you have this matrix is 1 by 1 and antisymmetric, so actually there are no central charges for the case of n equal 1. Now this algebra is invariant under a symmetry group, which is called the R symmetry group. Mathematically, this is called the group of automorphisms of this algebra. So it's a group of transformations that, if applied on the generator, gives you the same algebra. So this group rotates the n different species of supersymmetry charges into one another. If n is equal to 1, you just have a U1, R charge. And if n is larger than 1, you have, in fact, the UN, namely an SUN times U1R, the same U1R, except when n is equal to 4, we will see, in which case, in field theory, this U1 has an anomaly and disappears. So here is the algebra. And once we have the algebra, the next thing to do is to find its representations so that we know what the fields are and the multiplets are that our field theory will be built on. And the representation theory for massless particles and massive particles is different, and so we deal with them differently. So in the massless case, take a Lorentz frame in which the momentum is given like so. So we choose the space momentum to be along the z-axis, say. And if you write this out in terms of gamma matrices, then the dotted product of sigma and p actually in spinor space is a 2 by 2 matrix which has only a single non-zero entry. That's because this vector has square equal to 0, and that makes this object a projection operator. And E here, of course, is assumed to be non-zero, otherwise we have only the vacuum. So in fact, this means that if we call this second column and row the index 2, then in fact the charges for Q2 satisfy that Q2 with Q2 dagger is equal to 0. Now, in quantum field theory and in unitary representation theory of the supersymmetry algebra, Q better be a self-adjoint operator. And if the square of a self-adjoint operator, well, square in this complex sense, is equal to 0, then actually these charges are 0. So that means that effectively half of the supersymmetry charges are equal to 0. And then it follows that the central charges must also be 0, because the central charges can be viewed as the anti-commutator between Q1 and Q2. So you see that in the massless case, in the representation theory simplifies a lot. And now that we have this, we only have to deal with the Q1s anymore, and we have n of those. Now let's take the convention where Q1 lowers the helicity by a half, so then its dagger raises it by a half. So then if you look at this algebra, the remaining algebra on Q1, it's actually simply a Clifford algebra in dimension 2n. 2n because I have n complex Dirac matrices. So in fact, it's the Clifford algebra of SO2n, and we know its representations. It's just the spinor representations, but now with Euclidean signature. And so the smallest spinor representation is of dimension 2n, and there are two of those. So that's the representation theory. Now, if you want to do a field theory, then field theories are CPT invariant, and that means that you need a representation that is symmetric under the interchange of helicity and minus helicity. So for example, here I made you a little table. So the simplest case would be n is equal to 1. You could, of course, start with helicity 1 and apply the lowering operator once, and that would give you this multiplet. But this multiplet, even though a representation of the supersymmetry algebra, is not CPT self-conjugate. So you need to add also the multiplet with the opposite helicity. And so this is the full massless n equal 1 gauge multiplet because it contains particles of spin 1. There's also a chiral multiplet, which is a scalar in spin a half. I lifted the dimensions below here. And if we go up in n, then we encounter an n equal to gauge multiplet. Again, it has now one spin 1 particle, but then there are two Qs that allow you to descend from the spin 1 particle. So actually, there are two gauginos, and then there are also two scalars. And there's a hypermultiplet, which is the generalization of the n equal 1 chiral multiplet, where you have doubled up these entries. Now, in the case of n equal 3, you could write down a multiplet which has 1, 3, 3, and 1 here. But this, again, would not be CPT self-conjugate. So I need to add the other fellow here, 1, 3, 3, 1. Okay. And if we write down the n equal 4 theory, we see that here is its field count. In fact, these two things are the same. There's no distinction between n equal 3 and n equal 4 in super Yang-Mills theory. In supergravity, there can be. Any questions? Okay, well, having done the massless case, we swiftly move on to the massive case. And I think now you get the idea, so I'm not going to spend that much time on it. In the massive case, of course, we pick our momentum to be purely energy-like, and then we do not have this degeneration of the algebra. All the Qs now remain genuine charges, but in general, we can have central charges now. In general, this is a complicated matrix. It's anti-symmetric. It can, in fact, be semi-diagonalized in blocks of 2 by 2 anti-symmetric matrices in this way. So actually, you can characterize all of the central charge matrix by R complex numbers Z. And this number R, well, what it is depends on what n is. So it's essentially the integer part of n over 2. And now one can rearrange the supersymmetry generative Q, take this slightly bizarre combination, but somehow that is the right thing that does the job. And when you work in this way, you can combine the anti-commutation relations for Q and Q dagger with those for Q and Q, and put them all nicely together in the anti-commutation relations for these generators A plus and A minus separately. So the plus and minus here are all correlated with one another. Now the reason I exhibit this, this relation here is because it in fact naturally exhibits what's called the BPS bound. BPS stands for Bogomolny-Prasad-Sommerfeld bound, which originally came up in the study of monopoles, but then was actually realized that its natural setting is really in supersymmetry. So BPS is something that we will use a lot, which is why I want to explain it here. Now you see on the left side, if we set alpha equal to beta and I equal to j, then these Kronecker deltas are just 1 on the right-hand side. And on the left-hand side, I again have an operator anti-commuted with its adjoint. And this is always a positive operator. There may be 0 eigenvalues, but it is certainly never negative. So in fact, we know then that the right-hand side also must be a positive operator. So the mass operator plus or minus the central charge of Zi that we encountered here, these quantities must always be positive or 0. Which is what, now since m plus or minus Zi is positive, that means that m must in fact be larger or equal than the absolute value of Zi. So this is the so-called BPS bound. It's a very interesting bound because it tells you that if you just know the central charges of a state, okay, then you know a lower bound on its mass. That's very unusual. Now, the other thing that's important is that if we saturate this bound, if m is actually equal, let's say, to one of the Zi's, perhaps several of the Zi's, but let's say one of the Zi's, then actually for that particular Zi, the operators ai again square to 0. So effectively, they're not there anymore. You can effectively set them to 0. And we encounter essentially the same mechanism that we used in the classification of the massless representations. But now there is mass here. Okay. When that happens, you can see that since some of the a's are now equal to 0, when I construct my representation diagram by applying all the lowering operators, well, I have now fewer lowering operators because some of them were equal to 0. And that means that the multiplet of the representation is smaller or shorter. So in fact, whenever the BPS bound is saturated, one says that one gets multiplet shortening. The multiplet is shorter than you would expect if the mass did not satisfy the BPS bound. And this is, again, a very important concept. In particular, if I had a shorter multiplet, I don't really care how short it is, but if it were shorter, that means I have fewer states at that mass. Okay. Well, now suppose that I start computing corrections to this formula in terms of quantum corrections, loop corrections in quantum field theory. Well, you see there are fewer states at this mass level. Okay. If I wanted ever to change this formula and make the mass strictly larger than Zi, I'd need more states. But how could they ever come there? By continuity, you can argue that that can never happen. So in a sense, if a multiplet is short, then its mass is equal to Zi, even when you include quantum corrections to it. That makes this formula a very powerful formula because it is valid even when you include perturbative and hopefully even non-perturbative corrections. So it's a handle on non-perturbative physics, which is normally very hard to get. That's really the most important thing. The table, you have it, I have it, we all know it, you can deduce it, not a big deal. So far, this is all totally familiar. Okay. So now we have the representations in Hilbert space, so the next thing is to construct the fields. So for n equal 1, if we consider the gauge multiplet, the gauge multiplet contains the gauge field and the gaugino. Both of those are in the adjoint representation. Remember that supersymmetry commutes with colors, for example. So they're in the same representation. So what if the Lagrangian we can write down? Well, if we just had the gauge field, well, here is the standard Yang-Mills Lagrangian. We can, of course, add a theta term to it, because instantons do matter. And then there is a Dirac Lagrangian. But this Dirac Lagrangian now is actually for a fermion in the adjoint representation. Actually, if you make this Dirac Lagrangian gauge invariant, then it is automatically invariant under n equal 1 supersymmetry. You do not need to impose any further conditions. And just for the heck of it, I wrote out what the supersymmetry transformations are. So phi here is a constant supersymmetry spinner, supersymmetry generating spinner. So this is the Lagrangian for the gauge multiplet. And you can also have a chiral multiplet, which can transform in any representation of the gauge algebra. And I'm not going to write down everything here because we want to, move ahead towards n equal 4. And these Lagrangians get sort of bigger and bigger. N equal 2. Okay, well here we have a gauge multiplet that contains 2 Weyl fermions and also contains a scalar field in the adjoint representation. So in terms of the n equal 1 fields, it's an n equal 1 gauge multiplet and an n equal 1 chiral multiplet, all in the adjoint representation of G. For those of you who have looked at Seiberg-Witten theory, this is the arena in which Seiberg-Witten theory is played. There is also a hypermultiplet, which is an n equal 1 left chiral and complex conjugate right chiral multiplet. So early on, supersymmetry was sort of practiced a lot in the 2-component notation, which I always had a very hard time. It sounds all so different from, your usual Dirac equation and Dirac fermions and Dirac matrices. But when all the dust settles, really, the fields in a supersymmetric gauge theory are simply standard gauge spin 1 fields, spin a half, fermions, and scalar fields, which happen to live in a multiplet of supersymmetry. And the supersymmetric Lagrangians are really Lagrangians of these standard fields, but which happen to have special relations amongst the coupling constants and the fields. Okay, so finally then we come to n equal 4. So here I will be a little bit more explicit. So in the n equal 4 case, remember, there is only a single multiplet with spin less or equal to 1, which is the gauge multiplet. And so all the fields are in the adjoint representation of whatever the gauge algebra is. We have 1 gauge field. We have 4 Weyl fermions, lambda alpha. So alpha always refers to the spinner, 2-component spinner index, and A refers to the index that labels the different supersymmetries, 1 to 4. And then we have 6 real scalars, everybody in the adjoint representation. Now remember, in the case of n equal 4, the R symmetry was SU4R. There is no U1. It has an anomaly. It has a chiral anomaly with respect to these chiral fermions lambda. So it's not a quantum symmetry. And the under SU4, the gauge field is a singlet. The Weyl fermions transform in a 4, and the scalars transform in a 6, which is also, remember, SU4 is the same group as SO6 up to a factor of Z2. And so that 6 is actually the fundamental representation of SO6. We can write down its Lagrangian. Here are the standard pieces for Yang-Mills theory. Here is the Dirac Lagrangian for the 4 gauginos. Here is the kinetic term for the 6 scalars. All of these things are covariant derivatives with respect to the gauge field. And then to complete the Lagrangian and make it supersymmetric, we have a Yukawa term and a quartic term for the scalars. So the quartic term for the scalars is pretty simple. It's the commutator of any two of the scalars. And then this commutator is squared. And I really should have put a summation symbol here, sum over j and k. And the same here, of course. Well, all summation symbols have been suppressed. I think you can probably see that. So this is summed over I, and so on and so forth. And CIAB is a matrix whose I index is in the 6, and whose A and B indices are each in the 4. Both in the 4, not the 4 and the 4 star. So this is actually the Clebsch-Gordon coefficient for the tensor product of two 4s going into a 6 of SU4. This is an object you can easily write down in terms of the Dirac matrices of SO6. So this Lagrangian was constructed to be n equal 4 Poincare invariant. Notice, by the way, that I have not ever discussed superfields, not for the n equal 1 Lagrangians, not for the n equal 4 Lagrangians. The reason is not because I dislike superfields, but as you go to more supersymmetry, they in a sense become less and less useful. So for example, for n equal 1, you probably all know that there is a superfield formulation for the gauge multiplet and for the chiral multiplet, and you can write down any n equal 1 supersymmetric Lagrangian in a very standard way in terms of these quantities. And this Lagrangian is off-shell in the sense that you can compute the variation of the action and then obtain the equations of motion. For n equal 4, we are not so lucky because there is indeed a superspace formulation, but it involves Bianchi identities. And if you insist on the Bianchi identities in superspace, then the field equations follow automatically. So it is only an on-shell formulation. And that means that you cannot quite do Feynman diagrams in the usual way and so on and so forth because it's only on shell. You couldn't do a functional integral formulation because you do not have the ability to integrate over all fields, but only over the fields that are actually solutions of the equations of motion. So for that reason, and because mostly we'll be talking about n equal 4, I have not actually introduced any superfield language here. So let's look a little bit at the supersymmetry transformations. So there are 4 supercharges Q alpha and their 4 complex conjugates. I'm only going to write this down schematically. It is written down in many papers explicitly with all indices shown. The transformation of the scalars are the fermions. The transformation of the gauge field also is the fermion, but now complex conjugated. The supersymmetry transformation of lambda has a component which involves the gauge field. F plus here stands for the self-dual part of the gauge field, and it involves a commutator of 2 x's. You have to work out the group theory a little bit. Clearly, the group theory of the gauge group works fine because the commutator of 2 representations gives you, again, something in the adjoint representation. But the SU4 algebra also works out fine. I just let you do it. Not very hard. And finally, Q on lambda bar is the derivative of x. These formulas, at least schematically, will be important for what we do later on. Now, the last special thing about n equal 4 is that it has a symmetry which is conjectured, which is not really proven, so for the same reasons that I gave before. It's a symmetry from the late 70s, invented by Montonen and Olive, and called S-duality. And the symmetry group is somewhat unusual for a field theory. It's a discrete symmetry group, SL2Z. So this consists of 2 by 2 matrices whose entries are all integers, but whose determinant is 1. And what does this symmetry do? Well, you see, the Lagrangian involves the gauge coupling G and the theta angle. And these two objects can be put into a complex number, tau, in the following way. These pi's are just normalization factors. But the important thing is that it's theta and then I over g squared. I is root of -1. So this is a complex number. And in fact, the symmetry acts by Möbius transformations under SL2Z on this complex number. Okay. In particular, if you set theta equal to 0, and you pick, B and C to be 1 or -1, I forget, then in fact, this symmetry sends G into 1 over G. So it's, in fact, like the duality symmetry in the Ising model. It exchanges strong and weak coupling in this case. There is another component to the symmetry, which is that if theta is shifted by 2 pi, this is just the periodicity that arises from this theta term due to the fact that instantons have integer instanton number charge. So this is a non-perturbative symmetry. You could not see this in perturbation theory, because in perturbation theory, G is small, but 1 over G, of course, is then very large. But nonetheless, this symmetry is conjectured, and there is a lot of evidence for it, in particular from the spectrum of the BPS states of this theory. And this symmetry will also be important when we discuss string theory. Yes?
So why is it not proven? I mean, it didn't involve any of those fermions.
I'm sorry?
What stops us from trying to prove that with that Lagrangian?
Well, basically because this is a symmetry, I should have said this. This is a symmetry of the full quantum theory. Okay. And so really you would need to be able to define correlation functions non-perturbatively for all values of G and theta in order to verify it, if you wish. Okay. So that has not been done. What has been done is you can deform this theory a little bit, and then you can show that the BPS spectrum actually has this transformation symmetry. Any other questions? Okay. So now in the title was conformal invariance. So I just want to spell this out because we will also use this quite a bit later. The Lagrangian of n equal 4 theory, which we wrote here, classically is actually scale invariant. You know that from Yang-Mills, you know that from this term, and you know that for the Lagrangian of a Dirac particle that has no mass. So actually this Lagrangian is scale invariant. And well, all the dimensions, all the terms have dimension 4. The way you see that is the assignments for the scaling dimensions are A and X have dimension 1, the fermion has dimension 3/2, and the Yang-Mills coupling has dimension 0. Now, if you quantize this theory, by including perturbative corrections, it actually turns out that n equal 4 is ultraviolet finite. It's something that was proven a long time ago by Mandelstam and is also believed to be true non-perturbatively, even including the effects of instantons and other non-perturbative effects. So in particular, if it's ultraviolet finite, there is no dependence on any cutoff or renormalization scale that you put in. So it has a vanishing renormalization group beta function. Actually, you could amuse yourselves as a good exercise to take the standard table of, how much each field contributes to the one loop beta function and convince yourself that with this multiplet of n equal 4, the one loop beta function at least is equal to 0. Okay. Then you can go on to 2 loops, that's also known, but it's of course a little bit more complicated. So the proof here is not that this is true to only 1 loop or 2 loop, but actually is true exactly scale invariant even at the quantum level. Now in quantum field theory, if you have Poincare invariance and scale invariance, this implies conformal invariance, as I'll show in a second. Since in n equal 4 theory we have also supersymmetry, then the supersymmetry with the conformal invariance actually implies a much larger group, namely the superconformal group. And that's what I now want to exhibit. Now before I do that, since we're still on conformal transformations, let me, sometimes I will need to introduce snippets of knowledge, you know, that seem maybe a little bit ad hoc, but, you know, will come in useful later. So since we're on conformal transformations, let me just clearly make the distinction between isometries and conformal transformations. So if you have a manifold of dimension d, then a coordinate reparametrization, which is equivalent to a diffeomorphism on the manifold, is a transformation of the coordinates x to new coordinates x prime, which depend differentiably on the old coordinates x. Now often it's sufficient to consider these things infinitesimally. So then the new coordinates x prime are close to the old coordinates, and the deviation to first order is a vector field on the manifold M. So you all know from your relativity class that under a general diffeomorphism, the metric on M transforms in this way, or infinitesimally transforms with this characteristic symmetrized covariant derivative. So an isometry is a diffeomorphism that preserves the metric. So G prime is actually equal to G, or the vector field V satisfies this relation so that the change in G is 0, and this is called a killing vector. So V is a killing vector. Killing vectors generate isometries. A conformal transformation is also a diffeomorphism, but that preserves the metric only up to an overall scale factor, which may depend on x, may depend on the coordinates. It's conformal because this transformation preserves all angles, and that's after all what we mean by a conformal transformation. If I write it out, then G prime is equal to G up to a factor W, and the change in G, which is still given by this formula, is now proportional to the metric itself. And this equation is the conformal killing vector equation. Okay, so I think I will just flash through this. So if we apply this in flat Minkowski spacetime in dimension d, where the metric is like so, then of course you all know what its isometries are. There are constants, which are translations, and there are these rotations, or actually Lorentz transformations, which generates altogether Poincare symmetry, which is then an isometry of the metric. Conformal transformations include these too, but also have scale transformations or dilations, and a vector-like transformation, which is called a special conformal transformation. And these things form a group, which is SO2, D minus 1. If the dimension is 3 or larger, then these are all the conformal transformations. But in D is equal to 2, as you perhaps remember from your string theory or conformal field theory class, there actually is an infinite number. This is the Virasoro algebra in that case. But we're not going to be interested so much in this series of lectures in 2 dimensions. So now, if you have a symmetry in quantum field theory, for every symmetry generated, there is a Noether current. And in this case, these are constructed from the stress tensor. So for an isometry, well, in fact, in any case, the current is the stress tensor contracted with the vector field, either a killing vector or a conformal killing vector. And if we now check for covariant conservation, we obtain 2 terms, one which is involving the gradient, or the divergence of T, and another one which is like this. So if you have isometries, then conservation and symmetry of the stress tensor actually implies those. But if you have also conformal symmetry, then the trace of the stress tensor must also be 0. So in fact, you can now show that if you simply have scale invariance, that forces the trace of the stress tensor to be 0. But then when the trace of the stress tensor is 0, then actually the special conformal transformations are automatically a symmetry. So that justifies the statement that I made before, that in a Poincare invariant theory, if you have scale invariance also, then in fact you automatically have conformal symmetry. So now we are ready to discuss the superconformal invariance of n equal 4 super Yang-Mills theory. So n equal 4 super Yang-Mills has exactly vanishing beta functions. We're going to assume this now. Scale invariance implies conformal invariance at the quantum level. And in 4 dimensions, that conformal invariance is SO2, 4, generated by translations, Lorentz transformations, dilations, and special conformal. But now we also have supersymmetry. We have n equal 4 Poincare invariant, super Poincare invariance. If we combine this with the conformal symmetry, we actually obtain a superconformal group. The effect is that for every Poincare supercharge, we actually have a conformal supercharge. So we double up the number of supersymmetries. These supersymmetries again transform in the 4 of SU4 and of course are Weyl spinors. So when you put all of these generators together, conformal and the R symmetry invariance of n equal 4 theory and the n equal 4 Poincare supercharges and conformal supercharges, you get a superalgebra. And this superalgebra is actually, as a name, is SU2, 2/4. The 2, 2 arises because SO2, 4 is actually the same as SU2, 2 over Z2. This is like SO6 is equal to SU4 over Z2. So this is a non-compact linear form, real form of this group. So it's just like here. So that's what explains the SU2, 2, namely these generators form SU2, 2. And then the slash in the supergroup separates the bosonic part from the fermionic part. The 4 refers to the fact that there are 4 supercharges. And if there are 4 supercharges, then there also has to be an SU4 that rotates these supercharges. So in fact, the structure of this matrix is 4 bosonic entries in a sense and 4 fermionic. Here we have the SU2, 2. Here we have the SU4. And then here we have Q and S and, Q bar and S and Q and S bar. So the maximal bosonic subgroup of this is SU2, 2 cross SU4R. And this will be an important group. Now what is this P doing here? Well, you see, S normally makes the generators traceless. Okay. But the problem is that since there are just as many bosonic generators here as there are here, namely it's a 4x4 matrix in each case, and the supertrace is defined to have plus on the bosonic part and minus here, it is automatically traceless. So the P is actually a way of doing away with that extra piece that commutes and make this supergroup simple. Now there is one more thing I need to explain to you, and that is what the vacua are of this n equal 4 supersymmetric theory. So if we go back to the Lagrangian of the theory, here's the Lagrangian of the theory. This is all the Yang-Mills stuff. This is familiar. This is all fermions, a kinetic part. This is a Yukawa coupling. So the only term that's a potential for the scalars is this term that involves the commutator of the bosonic fields. Or the vacuum that is supersymmetric, then the energy, the Hamiltonian, should be 0 in that state. And that means the potential should be 0. So in other words, all these commutators should be equal to 0. That's what will guarantee that you have a supersymmetric vacuum. Now, the fact that the commutators are 0 does not necessarily imply that the individual x's have to be 0. In fact, it could simply be that the x's are non-zero, but all happen to commute. Okay. You can easily realize that by, for example, making the x's diagonal, if that's the right thing to do in that representation. So in fact, in general, if the rank of the Lie algebra is R, then the maximal number of commuting generators that you can find, or the maximal number of directions, is R. So in fact, generally, if you have a supersymmetric vacuum, then these commutators are 0, but the vacuum expectation values of the x's does not have to be 0. In fact, if these vacuum expectation values are not 0, generically, the Lie algebra symmetry is broken down to u1 to the power r. So that gives you r copies of n equal 4 superelectromagnetism, if you wish. And this is actually the arena of Seiberg-Witten theory for n equal 4 theory, when you have this spontaneous breakdown. Now you can see that if x is a dimensionful field, it has dimension 1. So if it acquires a vacuum expectation value, that breaks the gauge symmetry, but in fact it also breaks the conformal symmetry. It breaks the scaling symmetry, because this relation is not invariant under scaling transformations. Okay. So this is a case where you have spontaneously broken conformal invariance, not something that you have encountered very often, I think. Now, this is not going to be the case we want to be in, at least for the simplest version of the AdS CFT conjecture. Instead, the case we want to be in is when all the vacuum expectations of the scalar fields are equal to 0, and then the theory is genuinely superconformal and has unbroken gauge symmetry. So in other words, its symmetries are the gauge algebra, and this full P SU2,2/4 is unbroken. In this case, this group will be broken. It will be broken to the Poincaré group times some subgroup of this SU4, and still some supersymmetry. So this is in fact the context in which we will discuss the AdS CFT correspondence, at least until the last lecture, where we will then change it. Now, if this is a symmetry, if PSU2,2/4 is a symmetry, then that means that all the states and the operators in the theory actually can be classified in terms of the unitary representations of this group. Okay. So in fact, a lot of, and certainly the initial driving force behind this correspondence was the fact that you have this big symmetry group, and that you can test that, you know, various things on both sides are in fact invariant under this group. Yeah. Are these one?
Like I can see the classification.
Right. Yes, you can actually maintain this symmetry. And the key to that is that you can quantum mechanically maintain scale invariance.
So what about in the Coulomb phase?
Well, in the Coulomb phase, then they would still be supersymmetric vacua, but scale invariance is spontaneously broken, so it's not a symmetry anymore.
Yeah,
Well, if you quantize in perturbation theory, right, you could expand about this, you know, local classical minimum of the fields and do perturbation theory as usual, and you know, that would preserve the supersymmetry, and you would maintain, if you preserve the supersymmetry, and you may shift these vacuum expectation values a little bit, but if they stay non-zero, then you still have a spontaneously broken conformal invariance. So in particular, this theory has a massless dilaton somewhere, because that's the Goldstone boson for scale invariance. Does that answer your question? Okay, well, we can discuss more later. Any other questions? So then, in fact, the final problem that I want to address here is the construction and the nature of the superconformal multiplets of gauge invariant operators. So we're going to be interested only in gauge invariant operators. And for the moment, we'll be interested in operators that are polynomials in the fields. We could think of more general things like a Wilson loop or so, but for the moment, that's what we'll do. The fields will, as a result, have positive scaling dimension, because each of the ingredients has positive scaling dimension, and we could apply some derivatives, but a derivative has dimension 1 as well. So at least classically, all the scaling dimensions are in fact positive. Now, we can also easily compute the dimensions of the supercharges. Remember, Q anti-commuted with Q bar gives you P, the momentum, which has dimension 1. So actually, Q has scaling dimension 1/2. And S is its conjugate and has scaling dimension -1/2. So in fact, if you apply S repeatedly to the states in a multiplet, then repeatedly you decrease the dimension of this operator by 1/2, because the dimension of S is -1/2. But we had just argued that certainly, at least classically, every such operator has to have positive dimension. So that simply means that at some point, Q on this state, on some state, must be equal to 0. This is the same argument you use in the representation theory of SU2. When you have a finite dimensional representation, at some point, the lowering operator must be 0 on that state. Otherwise, your representation would go on forever. So we define a superconformal primary operator as an operator such that S applied to this operator is equal to 0. And it is primary provided it itself cannot be written as Q of another operator. And any state that can be written, or operator that can be written as the Poincare commutator of some other polynomial operator will be called a descendant state. So a primary operator is like a highest weight state in group theory. But here, the group is now this supergroup. So let's see how this works in practice. So we want to build some gauge invariant local operators. So they will be traces of products of these symbols: X, the scalar field, the Dirac field, the field strength, and the covariant derivative. But now we know, if we go back to the supersymmetry transformations, we know that the Dirac fermion lambda was actually the supersymmetry transform of the scalar. So it is a descendant. And we also know that the F plus part of the field strength is Q of lambda, so it's also a descendant. And we also know that the commutator of 2x's was one of the components of the anti-commutator of Q with the gaugino, so it's also a descendant. So that means, roughly speaking, that when we try to compute primary operators, in fact, whenever there is a lambda, an F plus, or a commutator of 2x's, we can toss those out, because they really are generated from descendants. You have to complete this argument a little bit more than I'm giving it here, but it's essentially true. And also, if you have a derivative on an operator, that's actually a conformal descendant, because if you wish, the double commutator of a Q would be P applied to that operator, and that means that it's just the application of a derivative. So in fact, now we have a pretty good sense of what the superconformal primary operators look like. If we limit ourselves to considering operators that have only a single trace over the gauge field, then in fact what we should do is, well, there's no lambda, there's no f. Gauge invariance does not allow us to include the field A itself because it's not gauge invariant. And there are no derivatives and no commutators. So in fact, we can have only a trace of a product of x's of the scalar field. And since no anti-symmetrization is allowed by this, in fact, the straightforward thing to do is to symmetrize completely over the index of SO6. Okay, so in fact now I'm going to discuss what these gauge invariant primary fields look like with respect to the full supersymmetry of the theory. So we have this huge group here, this supergroup, and we can label its representations. This is a property of supergroup theory by the representations of its maximal bosonic subgroup, which we can take here to be the Lorentz group times the dilation group, which is just R in effect, and SU4, which is the SU4 of R symmetry. Now you all remember how to label your finite dimensional representations of SO1, 3. You label them by 2 half integers. Okay. Just because if you complexify this group, it's really 2 copies of complexified SU2. And then SU4 is a group of rank 3. So the R1, R2, and R3 stand for the 3 Dynkin labels of a general representation in terms of the fundamental representations of SU4. So these R's, if you have a representation with highest weight lambda, then the R's tell you how to decompose that lambda onto the 3 fundamental representations. Okay. Now actually, we are going to use again this BPS type argument, but this time for this whole superconformal group. Before we had only used it for the Poincare supergroup. Yes?
Are you working on R3 or S3?
Excuse me?
Are you working on R3 or S3?
I'm working on R3.
Unitary representation.
Hmm?
How are you taking unitary representation?
A finite dimensional representation is what I meant here. Sorry. Did I say unitary? Yeah. Right. Okay. Well, there are 2 different things. We're going to, as in field theory, we're going to classify the fields according to finite dimensional representations of the Lorentz group, but then the Hilbert space states will be unitary representations of the whole group. So, in the case of let's consider this particular anti-commutation relation between the Poincare supercharge Q and the conformal supercharge S. This has dimension 1/2, this dimension minus 1/2. So this needs to close on the generators that have dimension 0. And let's assume that we are in a representation where we have a scalar from the point of view of the Lorentz transformations. Then these are the 2 generators, the dilation generator and the SU4 generator. So in fact, if we saturate the lower bound that we derive from applying the same BPS type argument here, we see that there is a bound on the dimension given by the representation characteristics of the SU4. So we can do this in the following way. Suppose I have a scalar, as I said, and consider representations with these Dynkin labels. Then if the dimension is exactly equal to that Dynkin label, then in fact half of the supercharges vanish and we have half BPS states. And the spins in the representation go from 0 to 1, 1, or spin 2. So these actually correspond to single color trace operators obtained by symmetrizing and making these tensors traceless. Sorry. I'm sorry?
You're saying you're using S as a commission conjugate of Q.
No. I did not write down the whole argument. You really need to play the same argument that I played for the Poincaré algebra. So you need to form linear combinations of this, that do the trick. I didn't write it all down here. Okay. So if this dimension coincides with the Dynkin label of this representation, then actually there is a BPS, then the states are half BPS, which means that half of their entries vanish. And if the dimension is larger than that, then in fact you have the full multiplet, which includes spins up to 2,2. So the next case up is when you have Dynkin labels of this type, L, K, L, and L is now not equal to 0, then if the dimension is K plus 2L, actually only 1/4 of the supersymmetry is preserved. And the spins run from 0, 0 up to 1, 3/2. And you can construct these operators as well by taking single trace operators, multiplying them together, working out the group theory so that it is given by this representation. And in general, this product then involves L anti-symmetrizations. It's true that you cannot use an anti-symmetrization in a single trace, but between different traces, you then in fact can. And finally, an even more complicated structure of the Dynkin label is like so. And when the dimension is like this, then in fact the operators preserve only 1/8 of all the supersymmetry. So a general classification of these representations was given a long time ago by Dobrev and Petkova, and then adapted to the case of AdS CFT by these authors here. So I want to end by saying that just as in the case of Poincaré supersymmetry, the mass of any of these BPS operators is not renormalized. I'm sorry, the dimension of any of these BPS operators is not renormalized for the same argument, by the same argument. Okay, and this I'm going to get to later. So in particular, we have explicit formulas for the 2- and 3-point functions in terms of the dimensions of these conformal operators. But this I will say a lot more about later. So, any questions? Questions? Yes?
Can two short representations join to form a long representation in this part?
When you tensor? Yes. Right. Exactly like in Poincaré, if you had, let's say two massless representations, together they tensor into, a whole series of massive representations. Yes.
Direct sum. I mean,
Oh, direct sum?
No, meaning like.
Yes, okay, I understand what you're saying. If you take two short representations that complement one another and would be two pieces of a long representation, yes, then by an infinitesimal change you could make it a long representation, which is not BPS. Just like if you take, left and right chiral together and give a mass, then you can, of course, yes, that's right. Any other questions? Yes?
So you said that for the BPS cases would involve several traces. Isn't it possible to have a single trace also?
No. If you have a single trace operator, let's see where it is. Right. if you have a single trace operator where all the indices are symmetrized and made traceless, that's automatically in this, yes, that's by group theory, automatically in this representation.
But would you be able to construct something that wouldn't be like, symmetrized? A single trace
In a single trace, let's see, so here's our single trace operator, right? And now you're saying if I had, for example, not symmetrized in indices, that would be a descendant, right? So that doesn't mean that that operator doesn't exist. It simply means that you obtain it by applying the generators of the superalgebra to it. So, you know, by the, what is this theorem called? The, not Phelps-Gordon, but I always forget. Anyway, if you know the behavior of the highest weight in the highest weight state in the representation, then you know all the other ones by you know, using the generators of the Lie algebra, superalgebra.
Thank you. If you have any further questions.
Okay. Thank you.